All right, today I'll be presenting Lab 3, Black Hole. So a general lab overview, we're going to go over the purpose of the lab and learning principles, setup of the GoScript model, analysis, and reflective questions. So what is the purpose of the lab? So we want to be able to derive the parallel, perpendicular, and net forces from the motion of a star orbiting a black hole. We also want to be able to manipulate the gravitational force equation to solve for an unknown mass. So initializing the program, our seed is obviously just going to be our Georgia Tech emails, and that's just going to give everyone a unique star path. And then you want to initialize the mass of the star and delta t with a given variables. How do we calculate the net force? As we know, F net is equal to delta p over delta t according to the momentum principle, and p is equal to mv. So over here, this code just demonstrates all of that. P initial is going to be the mass of the star times v initial, and the same thing for p final with v initial. Delta v is just going to be the change in v final, or the velocity and momentum, and then dp dt is just going to be delta p over delta t, and we're going to set that value to f net. So how can we find the parallel force? Well, what is the parallel force exactly? The parallel force is the force in the direction of motion, and it's the component of the net force that changes the magnitude of the object's momentum. So how we can do that is finding p hat, which is going to be p initial over the magnitude of p initial, which is going to give us the direction vector. And then we find the magnitude of dp dt, which is shown in this line. And then we set dp, or the parallel force, which is dp dt par, equal to the direction vector times the magnitude. Now, how can we find the perpendicular force? So what is the perpendicular force? Well, the perpendicular force is the component of the net force that determines the direction of motion. And since we know that F net is equal to the perpendicular force plus the parallel force, and we already know the values for the net force and parallel force, we can just do some simple algebra to solve for the perpendicular force, which is also reflected in this code right here. So how can we solve for the mass of the black hole? Well, by solving for m1 and using what we know to be true, we can calculate the mass of the black hole. So if we assume m1 is the mass of the black hole and m2 is the mass of the star, we can multiply r squared over, then divide it by g and divide it by m2, and we have the mass of the black hole. That's just represented here in the code with mass of the black hole is equal to the magnitude of the net force times the magnitude of the star's position times, or squared, and then divided by the universal gravitational constant times the mass of the star. However, since the position vector is constantly changing, and thus so is the mass of the black hole, we want to figure out a way to represent the average mass. So what we do is initialize two variables, idx and average mass, and then for every iteration through the loop, we want to add the mass of the black hole at that star's specific position to average mass, and then increase idx by a value of 1. So for every iteration, we'll increase the value of idx1 and then add the mass of the black hole to average mass. And that at the end of everything, we're going to return average mass divided by idx. So what this would actually look like in the GoScript program is something like this. As you can see, with every position, we're going to get a different value for the mass of the black hole. And then once it reaches back to its initial position, it'll return the average black hole as well as the values for the different forces. So what are the errors and potential improvements? So theoretically, there aren't being no errors because it is an online program and there's no room for like human error or unexpected influences. The actual model does imitate real galactical orbits given by the elliptical path taken by the star. The values seem relatively accurate given the initial values, and although it's obviously not a perfect model, with more specialized technology and programs that are not readily available to us, we can make more accurate models. So what does it mean? How are the net force and its parallel and perpendicular components different from the rate of change of momentum? Well, although we know F net is equal to delta P over T, which means they are numerically equal, conceptually, F net and delta P are obviously not equal. So F net is the unobservable forces, whereas the rate of change is observable. So what F net is it's the force that changes delta P, whereas delta P cannot do the same for F net. So F net influences delta P, not the other way around. So what if that instead of the black hole we currently had, we switched it out with a different black hole, but we kept the position of the black hole the same as well as the path of the star? Would that change the mass? No, it would not, because as we saw earlier, the mass of the black hole was determined based off of the positional vector. So if the path is the same, that means the positional vectors are going to be the same at every point, and thus so is the mass of the black hole. Thank you for listening.